the next presenter is Marc Dupuis. Marc Dupuis.
Yes, thank you.
He's a consultant specialized in mathematical modeling. Marc has degrees, PhD in chemical engineering in 1984. He's with Genesim Inc. since 1994. He's currently consultant since 94. Experience with mathematical modeling and design of HH cells, dealing with thermoelectrical, electromechanical, CFD, MHD phenomena as well. So welcome, Marc.
Thank you. So the subject of this presentation is back. It is I want to compare two type of result of the current density using MHD values, that is an MHD software, and then ANSYS, that is typically used for computing thermoelectric problem, to essentially further validate MHD values current density calculation, and so that's the main subject of, and then through the presentation, I'm going to present a case that is, the example I like to use is the Trimet cell that is in Hamburg, because it's a public domain bus bar, and we have used this model many times. And I'm going to try to improve the stability, not by improving the magnetic field, that is one way to do, but by reducing the horizontal current. And I'm going to use three ways to do that in sequence. And I will compare with ANSYS a result for the current density, because this is essentially improving the stability by reducing the horizontal current. So you need to be confident that you're computing correctly your horizontal current. Okay. And at the very end, I'm going to use the module of MHD values for alumina to see that the impact of improving the stability of the cell, the way we have done it, so by reducing the horizontal current, essentially reduce the flow, the intensity of the flow, and that has an impact on the alumina concentration. But it's an addition to the paper, not the main subject. Okay, so over the year, MHD we considered that it's mostly a magnetic field problem. So we designed the bus bar to have a nice BZ, so we have a stable cell. But the Lorentz force is it's J cross B, so the horizontal current has significant impact on cell stability, and they need to be also accurately computed. And unfortunately, we cannot measure horizontal current. There's no way to validate a model for horizontal current or current density in the metal, because there's no way to measure it. So my way to validate MHD values is to compare with a completely independent solution that I obtained with ANSYS. And then you see that the MHD values was designed to compute current density very quickly, because it needs to be recomputed every time step when you're doing the stability analysis. So you needed some improvement to not to compromise the speed, but to get a more accurate solution of it. Okay, so, and then also another point is that it's not only the y, but y is the side. So this is the cell, the length of the cell is the x direction, and the width of the cell is the y direction. So normally by using copper insert, for example, we are improving the jy. But the x is also important, so that's why I also want to discuss this, that we need, if you use a slice model to compute the horizontal current, you're going to compute only the y component. Yes, you can design the bar differently to reduce this y component, but don't overlook the x component. And this, at the very beginning, Gevry, when he computed the current density for the very first time in the aluminum industry, he was also considering the ledge of the and then the fact that the anode is not aligned with the cathode at the very first block, and he put insulation here, and then he also put the anode geometry correctly, and then after that we kind of lost maybe in our mind that the X component is also as important. It's not all designed that are producing 0 JX. Okay, so my example is the 3-met cell. So this is Hamburg. That's the 3-met cell. I'm going to use this as to illustrate the result. And first thing that is important to note, that's the bus bar. Now, it was retrofitted from a Reynolds technology to add 2 side riser and remove 1 end riser. But the way it was done, it is producing this current pickup. So it's not uniform current pickup. So that's generating some JX, horizontal current in the long direction of the pot. And if you want to compare with ANSYS, that MHD Valdez is solving the full bus bar network, so it's calculating this current pickup. The ANSYS model I'm going to use is only representing the cell without the bus bar, so I need to impose by current. So I need to compare, I need to use the same current pickup, so I'm going to use the one I'm computing with MHD Valdez. Okay, so that's I'm getting this horizontal current. That's the X component. The vector are both X and Y, but the color is the X component. So you see, you get 0.8 maximum value. So that's quite an intensive value of JX. And if you compute the Y, you get only 0.6. So you have more X component than you have Y component in this cell. Now, do you get the same if you do the same job with ANSYS? So ANSYS is it's a parametric, something that was developed a long time ago. It's a parametric model. You can represent any cell with it. So you decide how many cathode block you have, how many anode you have, what is the width of the channel, the end channel, the side channel, 1 bar, 2 bar, and you get, in no time you get the full 3D here. So I could do the 3-met, or I could do any other cell quite quickly. So if you look, the first anode is it's only covering half of the first cathode block. And then you have seen that the current pickup is not good. So this is what I have imposed, this current pickup on those collector bar. And this is what I get with ANSYS. So 0.8, same value, 0.6, same value. So this is, for me, the validation, because there's no other way to do it than to compare with another model, unfortunately, because we cannot measure that. And then this is, because the metal is so conductive, every discrepancy with 2 model or 2 geometry, everything will be picked up by the horizontal current. If you have more contact resistance, slightly different size of bar, slightly different sledge, different current coming from the anode, everything will go. Adjustment is done in a metal pad. So that means that this solution is very difficult. That's the way it is. The metal pad is doing the adaptation. So the current density there depends on everything you're doing. Now, the stability, that is the MHD Valdez, then will perform the stability analysis. That means you start with a perturbation on your steady state, and then you let the solution run for 1,000 seconds. And it was calibrated with the friction coefficient on the cathode surface to be critically stable at this ACD, that is 3.4 centimeter. So you get this critical stability. So it means that this is something new that was introduced here. It is the stability index. And in this case, it is very close to 0, because that's we calibrated the model to be critically stable in that condition. Now I'm going to improve the stability, so I want to be able to compare stability index of different situations. So I need to compute that. So it's a new feature in MHD values that now you get this number there. And then you can see it's quite close to 0. Let's mean that this, yeah, and you can see from the wave evolution that it is will stay there at that amplitude for forever. So that's the definition of critical stability. And now what I've done is that I adjusted in my model. I adjusted a contact resistance of the first collector bar to the flex, so that the first collector bar on both directions, both ends, is pulling a lot less current, about half of what it was pulling before. And I got rid of the JX this way. So that's the solution with MHD Valdez. And of course, I got a completely different current pickup for all my bars. So I imposed that solution to ANSYS. I got essentially the same solution. So I'm now confident that MHD Valdez and ANSYS, they are producing same solution for same setup. And now I want to know how much improvement I have achieved on the stability. So that's the next thing. As you can see, it's a bit more stable. Now I have to go fast because I think I'm running out of time. So next thing I'm doing is I'm doing partial rodding. So that's something that Pescini has done for the last 50 years. You don't rod up to the edge of the block. You keep the last 10 to 15 centimeter without cast iron. That's reduced the horizontal current intensity in the y direction, like we can see here. And if you do that in the ANSYS model, you get the same result. And if you run the stability from this new current density, you get the more stable cell. That new number here. And you can see now on that scale here that we are far from the 0 that we were at the beginning. So I have eliminated the JX a lot, almost completely, not perfectly, but and then I now reduce the JY. Twice I have improved the stability. Now I'm doing even more aggressive way to eliminate the JX, the JY. I mean, it is by having partial rodding. You could do the same by having copper insert, but I run here this with selective rodding that I've published like 20 years ago. And now, last year when I presented this, I got less stable cell, but at that time I did not get rid of the JX component. But now that I don't have JX and I've further reduced the JY, now I'm getting an even more stable cell. This number now here. So now, not only we can see that over the improvement, I can quantify my improvement, but you can see the effect of eliminating first the JY, the JX, and then the JY, and further improving the JY. So remember, JX is important, not only Y. And now I'm saying, okay, I have those solutions. I have an alumina module in MHD Valdez, so I ran the 4 case. And this is what I discover, is that improving improving the stability of the cell with the same feed logic, that also reduce the gradient, permanent gradient. The way this model works, it feed particle alumina, and then form a raft, and then the raft moved, and then the raft dismantled, and then you get the concentration of alumina based on the feeding. And here you can see that the feeder position that are symmetric. There's 4 of them, but the circulation, this one is covering only 1/3, and this one covering 2/3. So the 2 feeder on this side are feeding essentially 2/3 of the cell or growth, and then those 2 feeder, they're feeding 1/3 or so. That's why you build this big difference of grade concentration on this side compared to the other side. Now, if you change the flow by changing the Lorentz force, then you get a different flow. This, by the way, is a bad flow, not the metal flow. You improve the situation, but it was I observed that, but was not designed for that. I just improved the stability, and that was the outcome. So this is showing that yes, you could. Everything is coupled, and now improving the stability of the cell turned out to be also improving the situation of the concentration of alumina. And this I'm not claiming it's that in the real cell in the Hamburg, because it's until I validate this part of the MHD values, it could be far off reality. That's the story about modeling. You need to validate before you can trust your model. So conclusion, that I have further improved MHD values by comparing with ANSYS, improving the way that MHD values compute the horizontal current. That's mean the way he solved this problem. Now we are considering the temperature of the collector bar. So that I won't go into detail how we have improved MHD values, horizontal current calculation. What we did for sure, and then JY is X is as important as Y, and so you need to consider only both, not only because you have a slice model and you want to design a better cathode assembly. Disregard the X direction, because the X direction is important for cell stability. The current pickup and the way the first anode align or not align with the first cathode block and the ledge there in the corner, especially that I've not discussed this at all. And then that changing the flow also influenced the alumina concentration. So that's it. Thank you very much for your attention.
Thank you, Mark, for the very nice presentations. Now we have, I think, time for 2 questions. Open for questions.
No, I have one first.
Oh, you always cheat.
No, in fact, I have 2.
2? That's it? Nobody else?
Maybe 3. Okay, so first one, the dissolution, alumina dissolution model involved it takes into account the bubble?
No.
Okay, so that answer. Okay.
He's working on it.
Yeah,
but it's not there.
Yeah, okay, good. And the second one is, have you tried copper collector bar? Because copper collector bar, it will increase GX, and you're telling it's important. Have you tried in Valdes the difference between copper and
I've
copper?
not done any study on copper insert. MHD values can represent copper, and so you can put copper insert in MHD values as an input. I've not done any work on this myself.
Okay, so André.
Yes.
No, not written, only.
Revenging questions.
Thank you, Mark. Very good work. So, in one of the pictures that you've shown, the one...
It's gone, yes.
Yes, one of the pictures... This one.
Yeah, this one.
This one.
Yes.
My question is, why? You've computed the big reversals on JX here. Is this a... you have a big chunk...
On the edge?
Yeah, on the edges.
Yeah.
Is this an effect of the way that MHD Valdes represents?
No,
the
you see, it
wireframe
was the
network?
same in ANSYS. Almost the same. Not as strong, yes.
No, way less strong. This is what.
Okay.
That's why I'm asking. What is the reason for that? This discretization of the cathode?
Yes, you want me to say something about there's still a weakness in MHD Valdes on the X. You have improved the Y direction by having a finer mesh. And now you have also introduced, he's calculating the horizontal current in the cathode block itself. So if you have a different contact resistance along the bar, and you have some of the current will travel horizontally in the cathode block itself, okay? And that was the improvement of last year. If you don't calculate horizontal current in the cathode block, and you have contact, you do selecting rodding or you do incomplete rodding, some of the current travel horizontally in the cathode block itself. But in the X direction is still block and block and block, and no horizontal current is calculating in the cathode block in the X direction. And it is only one element per block. So it's still too coarse compared to JVRED, what it was doing in the 60s. MHD values is not there for the X direction yet.
Thank you all for the questions. Last question?
No? Okay, thank you.
Thank you. Thank you, Mark. Very good presentation.